Hello everyone, Sir Jules here, and in this video, we will be talking about our lesson 1.6, which is all about orbital notation. This is a continuation of our organic chemistry lecture series, and when we talk about the topic orbital notation, what is orbital notation? Orbital notation is like a visual representation of how many number of electrons is contained within each individual orbital of an atom. Now, in our previous topic, we've already discussed the energy level, the SPDF blocks. We're now getting to the more specific, which are the orbitals. The orbitals are like the basic housing unit that holds an electron within the entirety of an atom. Now, I've already discussed with you in my previous topic about the linear electron configuration. We should be able to master it already, as we would need that prerequisite knowledge in configuring our orbital notation. So without further ado, let's start by giving you an example. I have here an example of a nitrogen atom. What would be the first step, as I've mentioned previously, in configuring these elements or atoms? Correct. The first thing that we have to check is check on our periodic table. Now, looking at our periodic table, we see here that our nitrogen has the atomic number of 7, which means that it has 7 electrons. Now, I'll just write it down here so that we can keep track of things. This has 7 electrons. That is our first step. Our second step, correct, we'll write the linear electron configuration of this nitrogen atom. So if you remember our 1s2, 2s2, 2p6, we will be using that one in this lesson too. Alright, so since nitrogen has 7 electrons, we will start with 1s2, so that's 2 electrons, followed by 2s2, so that's 4 electrons. So we have 3 more remaining electrons, and that would be 2p3, correct. So this is a total of 2, 4, and 7 electrons. So this is our correct linear electron configuration. Now, as I mentioned earlier, that orbital notation is like the visual representation of where do this each individual electron is placed when in every individual orbitals of an atom. So think, in order to represent this, we have two main key things to remember. The first one, electrons are represented in half spins, which is represented by half arrows, both up and down. And second, the orbitals is represented in individual boxes. Alright, so if you can remember, the s orbital, the s block have 1 orbital, the p block have 3 orbitals, the d block has 5 orbitals, and the f block have 7 orbitals. So now, since we now have our lek, we will now try to distribute it in each boxes, which is the orbitals, to see where are the specific electrons located within the orbital of an atom. Alright, so if you can also remember with our previous topic with regards to the principles of electron configuration, we will also be needing that prerequisite knowledge in doing this also. Alright, so basically what we're just going to do is just, we have these electrons, these exponents, we'll just have to distribute them on each of these boxes. But we have specific rules to follow. The first one is the Pauli's exclusion principle. So this is just a review since I've already discussed this in a different video. Pauli's exclusion principle states that no two electrons in the same orbital could have the same spin. So it could either be the one is half arrow up and the other is half arrow down. So they are in opposite spins if they are in the same box, because that is an orbital. Now, the Hund's rule states that in order to fill out all these orbitals, we have to fill all of them one by one with each individual electron before we go on pairing another electron within a single orbital. So think of it in this way. Just like when you'll be riding a bus, an empty bus. When you ride on a bus, you always take on the seat that's unoccupied, right? And then when all spaces have been occupied, that's only the time that the next person boarding the bus will sit next beside you because there are no more seats available that are unoccupied for them to sit on. So that's just basically the concept. Alright, so to give you a graphical representation, this first orbital is the 1s, second is the 2s, and this is the 2p orbitals. Remember, the p has three orbitals. This is the px, py, and the pz orbital. Pz rather. Now, in doing this, the next step is that we have to fill the orbitals with the electrons. So for the 1s2, they have 2 electrons. As you can see here, they have 2 electrons. So that is 1s2 and then 2s2. I mean 1s1 and then 1s2. And then followed by the 2s2. So this will be the 2s1 and then 2s2. Then followed by the 2p3 orbital. Now, why is this specific example incorrect? So let's take a look. Hund's rule states that we should occupy all the orbitals first before we sit another electron beside another electron. So in this case, since we have 2p3, that's 3 electrons, it should be 2px, 2py, and 2pz. This electron right here should not be in there. That should be on the third orbital because that electron should occupy first all of the orbitals before sitting with another electron. Alright, so the same thing here. That's why this is our correct orbital notation of the nitrogen atom, because it obeys all the principles of electron configuration, and we have the correct linear electron configuration for this one, P3. So this is correct. Alright, so let's further give you examples so that we can master the topic of orbital notation. So I have here 3 elements which we will be doing a practice drill or just doing their examples so that we can also learn further regarding orbital notation. Now we have phosphorus, we have sodium, and we have boron. So what is the first thing in configuring these elements, as I've discussed previously? Always check your periodic table. Now for phosphorus, we have 15 electrons with the atomic number 15. For sodium, we have 11. And for boron, we have 5. Alright, so just to keep track of things, we always have to write it down so that we can always double check if we're doing the correct thing. So phosphorus is 15 electrons, sodium is 11 electrons, and boron is only 5 electrons. I'll just write it down here on our whiteboard. I'll just copy it. Phosphorus has 15 electrons. Sodium has 11 electrons. And lastly, we have boron have 5 electrons. As a first step, what should we do since we now have all of these electrons? We should write their electron configuration. So I've already given you a mnemonics for this one on my previous video, so check it out. And so that we'll be familiar with what is the flow for the linear electron configuration. So since we have 15 electrons, so this will be 1s2, 2s2, 2p6, 3s2. How many are there already? So there are 2, 4, 10, 12. So we need 3 more electrons. And that would be 3p3. So that's 3, 5, 11, 13, and 15. So this is our correct linear electron configuration. Now going down to our orbital notation. I would suggest we do this in this manner so that for those beginners you can keep track of your progress. So you'll just write each orbital under their respective linear electron configuration. So for S, you only have one orbital, right? In other S block, we only have one orbital. The P block, we have three orbitals. 1, 2, and 3. Now, the S, we only have one orbital. And another P, we should have 3 orbitals. Now, to represent this one, we have 2 electrons. So this should be occupy all the orbitals first, since S only have one orbital. So they would sit alongside each other. That's 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3. Now, all of the orbitals are now occupied. Let's go back to the other and fill them out by pairing them with each other. 2p4, 2p5, and 2p6. For the S, through the 3s orbital, this is 3s1 and 3s2. For the 3p, finally, following the Hund's rule, occupy all of them first. This will be 3p1, 3p2, and 3p3. So let's check. There are 2, 4, and this is 6. So that's 2, 4, 10. This is 2, so another 12. Then 12 plus 1, 2, 3. That is 15. So this is correct. Alright, so let's get down with another to further practice. For sodium, we have 11 electrons. So let's do the linear electron configuration. 1s2, 2s2, 2p6, that's 10, and 3s1. So now, we now write down or draw the orbitals. This is for the s orbital. This is for the 2s orbital. This is for the 2p orbital. There are 3 orbitals. And for the 3s orbital. Now, since we now have all of these drawn down, so let's now write the respective electrons. I used another color just to not confused. So we have 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, and then 3s1. Now we have a total of 2, 4, 10, 11 electrons. So we have 11 electrons, and we didn't violate any principles. So this is correct. Alright, so getting down to the last but not the least atom that we'll configure for today. So this is the boron with 5 electrons. This will be 1s2, 2s2, and 2p1. A total of 5 electrons. Now we draw down all of their orbitals. This is for the 1s orbital, the 2s orbital, and the 2p orbital. Now, let's now distribute the electrons to each of their orbitals. 1s1, 1s2, 2s1, sorry, this is 2, 2s2, and 2p1. So even though if we only have one electron for the p orbital, we should always write all of the 3 orbitals to represent that it's within the p block. All right? So we have 2, 4, and 5 electrons. So this is correct. All right, so that's it. That's our orbital notation. So it's just basically a visual representation as to how many electrons is housed in each orbital of an atom. Alright guys, so I hope you learned something from this video, and I'll catch you up on the next one and see you. Thank you so much. Bye-bye.